Hey guys, Dr. Betts here coming out with another fantastic chemistry video, and today talking about dipole moments. Pretty big topic, pretty simple topic, but very important for you to understand. So let's get into it. Here we have molecules molecules that are in increasing polarity. Let me get myself out of your way here. There we go. So over here we have a non-polar molecule, ethane. Ethane does not have a dipole moment. It is non-polar. Non-polar molecules do not have permanent dipole moments. But now here's methylamine. You may remember it from such shows as Breaking Bad, where they stole it from the train. If you haven't seen the show, sorry, spoiler alert. Anyway, methylamine has a dipole moment. How do I know? Well, first of all, there's an arrow like that over it. So if you're talking about dipole moments, a lot of times you're going to see arrows like that. And these are called dipole arrows, where this part of it is towards the delta positive, this part is towards the delta negative. These are called dipole arrows. There, make that a little cleaner. There we go. Dipole arrows. Well, why does the arrow, or why is this nitrogen delta negative? Because it's more electronegative than carbon. So it's going to pull electron density towards the nitrogen. Now, methanol has an even larger dipole moment. This oxygen is delta negative, the carbon is delta positive. Why is it larger than methylamine? Because oxygen's more electronegative. Okay? More electronegative. Chloramine also has a dipole moment. Delta negative, delta positive. And of course, you have your ionic bonds. Molecular dipole moments. Now, we're not going to get too much into the measurements of dipole moments. That's not really what this class does. But what we need to do, we need to understand and come to grips with is where the delta negatives and where the delta positives are, which is why I really like this example right here. Notice the dipole arrow right there. Let me just pull up my laser pointer. Right here. It's pulling towards the chlorine. Now notice the relative size of the arrows here. This arrow is large. These arrows are getting progressively smaller. Okay, as you move away from the electronegative atom, the dipole arrows get smaller because the delta positives get smaller. Okay, now what's happening here is the carbon is losing its electron density to chlorine. Chlorine is literally pulling it through the sigma bond in a process called induction. We'll come back to induction at a later time. So it's pulling electron density this way. Now this carbon then is becoming delta positive. So it's now a little bit more electronegative than the hydrogens that are surrounding it. So it will in turn draw more electron density from those hydrogens, making the hydrogens delta positive. So the carbon is delta positive, and so are the hydrogens attached to it, or any atom that's attached to that carbon will become delta positive, of course, except for the delta negative chlorine. Take a look at this one. Okay. The more and more electron density pulling that way makes this hydrogen a little more delta positive. Not a big deal. I'm not trying to get too much into the nitty-gritty with dipole moments. I just want you to understand that the electronegative chlorine pulls density towards itself, thus causing more delta positives at remote locations. It's 3 bonds away actually is the limit. So big dipole arrow here, smaller dipole arrows here, small delta positives out here, big one at the carbon, big one at the chlorine, delta negative. Okay? And here are just what are called electron maps. Basically what you're seeing is how much negative charge is on the end here. So the nitrogen has a fairly good red spot there. Oxygen's a lot more red. Here's carbonyl. Carbonyls are definitely, the oxygen is definitely going to be red. And the nitrogen of a nitrile is definitely red. They're delta negative, okay? Oops. Okay? So it's important that you can identify where the delta positive charges are and where the delta negative charges are. For example, if, say, we had methyl chloride and we gave it something Oops, I'm in the way again, aren't I? Let me move myself. something negative. Let's just say negative. Let's just say neg. And this is delta positive, the carbon is. This is delta negative. Where is that thing going to collide? What atom is it going to hit, essentially? It's going to hit the carbon, right? It's going to be repelled by the chloride, and it's going to be attracted by the carbon. So it's going to slam into that carbon. It's probably going to repeatedly slam into it. Why? Because they have opposite charges. Okay? So there's going to be a collision, 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 collision. What are the three things required for a chemical reaction? Molecules must collide. Molecules must collide at the right orientation with enough speed or activation energy to make a reaction happen. That's what has to occur. All right? And with that, I'm going to leave it here. We're going to come back in the next video to talk about intermolecular forces. You have to understand dipole moments to understand intermolecular forces. Okay? So with that, I'm going to wish you all good luck and good chemistry. We'll see you soon.